This video is covering Riemann sums and particle motion problems. So Riemann. Riemann is kind of weird because, or the name is kind of weird because it's the name of some guy way back when who discovered this, and that's who it's named after. So what Riemann sums do is it allows us to talk about accumulation. So if I'm giving a rate of change, let's say velocity for instance, and you were given different velocities at different intervals, then you could accumulate how much distance was traveled. So we're going to start off with a very, very basic problem. So if I'm giving you the graph of velocity, make sure you are paying attention to what you're given the graph of. So we're given the velocity, and for this example, feet per second, of a particle traveling along the x-axis. Now, the graph that you're looking at is not the path of the particle along the x-axis. It's talking about the distance traveled on the x-axis, moving left and right along this x-axis for 10 seconds, so from 0 to 10 seconds. All right, so when the particle starts out at time 0, then it's looking at a velocity of 20 feet per second. So this is talking about, this graph is looking at its velocity, not its position. So for the first 3 seconds, this particle is moving with a velocity of 20 feet per second. Okay. Then at 3 seconds, it automatically jumps down to a velocity of 10 feet per second. It stays constant until 5 seconds. So then at 5 seconds, it drops down to negative 20 feet per second. So again, negative, for those of you not in physics C, negative velocity just means we're now moving in the opposite direction. So, so for positive 20, we're moving to the right, positive 10, we're moving to the right, and then at 5 seconds, the x is changing direction, now moving to the left with a speed of 20 feet per second. All right, and it stays that velocity all the way until the end of the time period. Okay, so what our question is now is how far and in what direction does the particle travel on each interval? So if you just look for 0 to 3 seconds, and remember, that just the basic distance equals rate times time. So our rate is in feet per second, and our time is in seconds. So when those units cancel out, when we multiply, we get just feet. So if we look at this, we have our y is a feet per second. So for this first interval, for those 3 seconds, we have a rate of 20 seconds. And then we have a time of 3 seconds. So that is going to be, if you look at this pictorially, you have a graph of a rectangle. It's the area of a rectangle, length times width. So if you look at this on the units of the graph, you've got a 20 by 3 rectangle. And together 20 by 3 is 60. So if I were to do that same thing with my rate times my time, so if I'm traveling at 20 feet per second for 3 seconds, then I have traveled for 60 feet. So graphically, that is represented by the area under the curve and the x-axis. So we have 20 by 3, which is 60 feet. So that's kind of the connection that we're making today. So for the first 3 seconds, this particle has moved along the x-axis for 60 feet. Then from 3 to 5 seconds, its velocity is now at 10 feet per second. For 2 seconds. So if you look at this box here, we've got a velocity of 10 for a time period of 2, so that would be 20 feet is the accumulation. We call it accumulation of distance there. So 10 times 2 is 20 feet. Okay. So for the first 3 seconds, it's traveled 60, and then it's traveled 20 more, so we now have traveled a total of 80. Now at 5, it changes direction. It abruptly changes direction. It is now going to the left at a speed of 20 feet per second for an entire 5 seconds. So again, you can see it's 5 seconds long. It's negative 20 in velocity, so that's going to be a negative 100 feet. So negative 20 is my velocity, 5 is my time, so negative 100 feet. So what that really means is it travels for 100 feet, but it really travels for 100 feet to the left. So we have 60 feet to the right, then we have 20 feet to the right, and then really this should be, this means positive feet to the left. Okay? All right, so now the next question is, how far and in what direction is the particle from its starting point at the end of the 10-second interval? I don't know where I started. We can assume it's 0. But if we traveled for 60 feet to the right, so we're going to call that a positive distance, and then 60 feet, or 20, plus 20 feet, and then we backtracked 100 feet. So what that ends up being is 80 minus 100, which is negative 20. Now, you don't want to say negative 20. I mean, you could say its displacement is negative 20, but we would say 20 feet from, sorry, 20 feet left from the start. Okay, so that is, when I talk about how far is the particle from its starting point, we call that displacement. All right, but then there's another important question, is what is the total distance? Because it didn't travel 20 feet. It ended up 20 feet away, but it actually traveled and covered more distance than that. So the next question that we want to ask is, what is the total distance that it actually travels? So it traveled for 60 to the right, 20 to the right, and so when I want total distance, what that means is looking at its speed and not its velocity. So remember, speed is the absolute value of velocity. So if I'm looking at the total distance, then I need to take the absolute value of each of these distances. Okay, so that would end up being 60 plus 20 plus 100, which is a total distance traveled of 180 feet. Okay? All right, so make sure you understand the difference between how far a particle is from the starting point, its displacement, and its total distance. Okay, so essentially what we did right there, and you might have done this before in physics, but this is actually something has a name. Sorry, it's called a Riemann sum. So what we just did was called a Riemann sum. Now you typically won't see ones about this basic in calculus. So let's see what it will actually look like in calculus, what a Riemann sum looks like. All right, so here's a curve, which is typical of what you would see in a calculus problem. It's not just straight lines like we saw in the first problem. So what I'm going to do is I want to calculate the area that's underneath this curve. In other words, I want to figure out what is all of that, okay? Because that would be called our accumulation. Because if this again was velocity, if this was a feet per second over here, and this was seconds, then if you multiply feet per second times second, then what you get all of that inside is your total distance traveled, your feet, okay? So when we did the first example, we were finding the accumulations of these rectangles. We were finding the area between the line and the x-axis. So we want to do that, but now these were easy because they were just rectangles. So rectangle is length times width. But now we have a curve. So how do we find the area under a curve? Well, from what you know right now, you cannot find this area that I've covered in green. But what we can do is what we use a Riemann sum for. So I'm going to erase that for a second. And what Riemann came up with is, well, you could find a good estimate of the area under the curve by using rectangles. So if we split this up into sections, so let's say if I have an interval from 0 to 12, and we want to have 4 sections of equal width, then that would be a width of 3. So if I look at these 4 sections with a width of 3, then you can make rectangles out of those sections. So if you look at this one, this is what's called a left Riemann sum. And the reason it's called a left Riemann sum is because when I separate these 4 sections, the rectangles, their heights, are governed by their left endpoints being on the curve. So if you look at this first rectangle, where is it hitting the curve? It's hitting the curve here. The second rectangle, it's hitting the curve. Its endpoint is hitting the curve here. This endpoint here, and this endpoint endpoint here. So if you look to the left of each of those rectangles, then you are hitting, sorry, if you're looking at left of each of those rectangles, then you're hitting the curve with those endpoints. Okay, so that's called a left Riemann sum. All right, so a couple of things you need to make sure and watch out for is, first of all, what's the width of each rectangle? Because what I'm doing now is, instead of accumulating the entire area under the curve, I'm now accumulating the areas underneath these rectangles, which, as you can see, is not going to be exact, but it's going to be pretty close to the area underneath that curve. So the width of each rectangle is actually uniform width. So I'm going to say that this is uniform width of 3. Okay. Then what is the height of each rectangle? Now I don't have y values, I don't have a function. So the height of each y value, if you look here, if this was 0, then the left endpoint right here would be at 0. So the height of the first rectangle would be whatever the y value is at 0. The height of the second rectangle would be the value of whatever f of 3 is. Then the next one would be f of 6, and then the final one would be f of 9. So I have 4 rectangles, so I have 4 y values. You can notice, though, that for 12 hits the graph here, and you can see that there's no rectangle that has its endpoint hitting at 12. So we don't need f of 12 for this problem. So if I want to find a left endpoint Riemann sum with 4 equal subintervals for f of x in the interval from 0 to 12, what we do is we add up those rectangles. Rectangle 1, it has a width of 3 with a height of f of 0. Plus, rectangle 2 has a width of 3 with a height of f of 3. Rectangle 3 has a height of 3, or a width of 3 with a height of f of 6. And rectangle 4 has a width of 3 with a height of f of 9. Okay, so if you were to, you want to see that written out a little bit more, I'm really just adding up the areas of these 4 rectangles here. Okay, so that is an expression for a left Riemann sum. Now you can definitely simplify this a little bit more. Since we have uniform width of 3, you could simply take the 3 out and write it like this. But a warning to you, not all Riemann sums have uniform width, and then you would have to write it out separately. So that is what a left Riemann sum looks like. All right, so now what if we take the same exact function, but now we talk about a right Riemann sum? So look at the difference between these two graphs. I still have the same interval sections sectioned off. But now, with the first rectangle here, I have my left endpoint. But now, for this section of the rectangle, the right endpoint is what I want to know where it's hitting the graph. So that's going to govern the height of that rectangle, is the right endpoint for each one. Okay, so the right endpoints are now hitting the curve, and so this is called a right Riemann sum. So the width of each triangle here, or rectangle, I'm sorry, is still a uniform width of 3. But now the heights are a little bit different. If you look now at f of 0 is not an endpoint. So our first endpoint is f of 3. So our first rectangle now has its endpoint at f of 3, then f of 6 for the second, then f at 9 for the third, and now you can see 12 is the rightmost point, and it now has a rectangle. Okay? So to write the Riemann sum for this, if I were to accumulate the area here, again, we would add up the areas of each of these rectangles. So since we have a uniform width of 3, I can just multiply that outside and just add up f of 3 plus f of 6 plus f of 9 plus f of 12. All right? So typically we'll either have a function where you can evaluate those y values, or you would have like a table that would tell you the y values, and you can actually find this stuff. All right, so let's look at just a couple of problems with Riemann sums. So here we have a table with no graph, and it says a particle travels along the y-axis, so that means the particle is moving up and down with velocities given in the table. Find a right endpoint Riemann sum for the velocity with our change in time equaling 1 second. So what that means is our change of time, our uniform width is a distance of 1. So what that means is uniform width of 1. Okay? And then tell what it represents. So if we're finding a right Riemann sum, then we want to find all the rightmost endpoints. So I have these 3 sections here, and I want to use the rightmost values. So the rightmost values are going to be these values here. So those are rightmost values. So what that means is we're not going to be using the leftmost value of 10. Just like we did with the example of the right Riemann sum here. We used all the rightmost endpoints, but we did not use the leftmost of 0. Okay, so to calculate this, we have a uniform width of 1. So I'm going to multiply 1 times, now we're going to add up each of those velocities. So the velocity at 1 is 7 plus 5 plus 4. So that's, what is that, 12, 16. Okay? So that is 16, and we want to tell what it represents. So if we multiply feet per second times second, then we get feet. So what that means is the particle travels, or it has a displacement of 16 feet on the y-axis. So that means its displacement is 16 feet on y-axis. Or we could even say, just to say where above the x-axis, if we want to be very specific. Okay? Now, this might be kind of confusing for some of you because there was no graph. So what you can do, if you want to, you can create your own graph if you want. So 0, 1, 2, 3. We have seconds, and we have feet per second. And let's say this is 10, 7, 5, 4. So 0 at 10, 1 is at 7, 2 is at 5, 3 is at 4. Now I don't really know what's going on or exactly how this looks, but we can kind of pretend, and if you were to do a right Riemann sum, then for each section, so if we sectioned these off, then for each section you would use the right Riemann sum. So it would look like that. Okay? So if it helps you to draw a picture, then go for it. Draw a picture. That's totally fine. All right, so our last example, example 2. We have the same scenario going on here, but this time we're traveling along the x-axis with velocities given in the table. So we want to find this time a left Riemann sum given uniform width of 2 and tell what it represents. So the leftmost values are going to be these values, so we don't care about the -3. All right, so to find the left Riemann sum, we have uniform width of 2, and you can see that here in the problem, uniform width of 2. So 2 times 4 plus 1 minus 2, so that's going to be 2 times 3, which is 6 feet. Okay, and that's a positive value, so that means we have a displacement. This particle is moving along the x-axis. We have a displacement of 6 feet to the right is where we end up. Okay. Again, you could draw a graph if you wish. And then for part B, it says find the left endpoint Riemann sum for the speed function. So the importance here is remembering that velocity, which we have here, can be negative. All right, but since now we're looking at the speed will be positive there. So when we're looking at the Riemann sum for a speed function, you're not looking for displacement, you're looking for total distance traveled. So all you have to do for that is use the absolute value. So you have 2 times, 4 was positive, 1 was positive, and all you have to do is make 2 positive. So this is going to be 14 feet. So the total distance traveled is 14 feet. Okay, now there's something that I do want to clarify that I'm actually skipping that you actually really need in your problem. So what I'm missing out is being very specific with my times. So for these two answers, for part A it says the displacement of 6 feet to the right during the time interval from, what was it, 0 to 6. And that was in seconds. You want to be very, very specific in your answers. So that's part of that technical writing. So the particle has a displacement of 6 feet to the right during the interval from 0 to 6 seconds. And the same thing here. The particle has total distance traveled is 14 seconds on the interval from 0 to 6 seconds. Okay, so that is your basic left and right Riemann sums. There are more type of finding those sums, but we'll talk about that in another lesson.